So the agenda is that I'm going to run through these things really quick. Maybe not all of them. Just hit some main ideas to make sure you know everything that's included, everything you need to do for these LOL charts. I already did number 1 on the last video, so I'm not going to do that again. Okay. We got number 2, a can of cold soda. So listen, step 1. What is step 1? Anybody tell me? Wrong? Soda. Identify the system. What are we talking about here? We talking about the can? We talking about the cold? The soda? Warms? Counter? What are we talking about? Soda. Okay? That's what we're concerned about. That's the system. That's what we want to know. Is it gaining energy? Is it losing energy? What is it doing? That's the center of our attention. That's our focus. Everything outside of the can of soda is referred to as the surroundings. Okay, now what should we do? Do the initial phase, okay, initial state, sorry. I just gave away the answer to my next question. Which one's easier to do first, do you think? It doesn't really matter. I like to do phase, I guess. I like to do phase first. It's just easy. Can of cold soda. So if we're talking about the soda, what phase is the soda in? Is it solid, liquid, gas? What is it? Liquid. Okay, so for phase, the number of blocks we use tells us the phase. We use 1 for solid, 2 for liquid, 4 for gas. So since we said it is a liquid, I'm going to do 2 blocks, and we're good. Now at the end, if it's left on the counter, is it going to be a solid, liquid, or gas? Still going to be a liquid, right? So still 2 blocks. So there we go. All right, now thermal energy, how does it start? Is it cold? Is it room temperature? Is it warmer than room temperature? Is it really hot? What's the deal? Okay, it's cold. So cold is 1 block, room temperature is 2, warmer than room temperature is 3, and then really hot would be 4 blocks. Okay, as it's left on the counter, over time, what is the temperature going to go to? It's going to go to room temp. So I'm going to go 2 blocks here, and now we've got our blocks made. Now let's just count them. 3 over here, 4 over here. Well, if we had 3 before, and we had 4 here, what happened? Went up by 1, okay? So that means our system gained 1 block of energy. So I'm going to draw a block on the edge here, and I'm going to draw an arrow tip that shows that the energy is going in. I also like to draw a little Q here to show that it is heat, because that's the way energy is being transferred. Every time we do one of these problems, it's going to be heat. All right, next thing we got to do, we got to talk about the particles. Let's talk about the arrangement. What's the arrangement going to do? It's going from liquid to liquid. Okay? Yeah, I mean, there might be if I said there's a small amount of change in the arrangement, what would you be likely to say? I would say just maybe. It's not changing phase, so the particles aren't going to change much. But they might be slightly more spread out because it is warming, but I'm not going to say not much change there. Maybe slightly more spread out. And then so arrangement with that, we're going to think of phase a lot. Maybe a little bit with the thermal energy. So motion, what about the motion of the particles? They're going to be moving faster, aren't they? Moving faster, more collisions. Again, that's going to lead us to having slightly more spread out particles. And the last step, anybody remember what the last step is? Is it endothermic or exothermic? Okay. Endothermic, why? So the prefix endo means in, inside. So we're saying that the energy is going inside, which makes sense when we look at our arrow over there. And so we should be able to say, by looking at this diagram, exactly how the energy transferred. We know it transferred by heat. We know it transferred from the surroundings to the soda. So what would be the surroundings for the soda? Can anybody tell me that? Air. Counter. Can. Good. All right. So that's what we do for each one of these. Okay, so what was number 3? Is that going to be exothermic, endothermic? What is that? It's exothermic. You put water in the freezer, and it's going to lose energy to the air in the freezer. Okay. Number 4. So I wanted to change this one to the system in number 1. Now, if we talk about this, if we have the coffee cup sitting on the counter, and it's cooling, right? It's going to cool down to room temperature. So the energy from the coffee is going to go where? To the air. So is it going to heat up the air particles? Yeah, it is. Is it going to affect room temperature? Why? Yeah, it's not a lot of energy that it can transfer in a cup of coffee. Okay? You start a fireplace and you want to burn some wood. Yeah, that's going to affect the room temperature. A cup of coffee? No. Can you tell that it's releasing energy to the air? How? Okay? You can see some steam a lot of times, or just do what? Yeah, hold your hand over a cup of coffee. I do that when I'm cold in the wintertime. Put my hand over my cup of coffee. Warms me right up. Yeah. So with that example on number 4, the thing you got to think about in terms of energy in a system, and this was in the notes we talked about, it's not just about how hot something is, but it's also about the mass, which we're going to be talking about more over the next couple days before our test on Friday. Okay. On this number 5, what you're supposed to do, I know some people were confused by number 5, but what it's saying is you've got ice cubes described in number 3, you put them in a soft drink. And do the energy flow for this LOL chart, just like we did the other ones. What it means is, one time, think of the ice cube as the system. So how is the energy changing? Is it an exothermic process? Is it an endothermic process? And the other one, think of the soft drink. What if that was the system instead? Main idea, a couple main ideas on this. Number 1 is good understanding of system and surroundings, and why it's important to identify the system so we know what we're looking at and what would be the surroundings. And the other thing is that we should have saw, potentially, depending on how you did it, we should have saw that the energy that the ice is gaining should be equal to the energy the soft drink is losing, right? Because they're transferring energy to each other. Now, based on the bars, that may not have worked, and that's okay. But that's kind of the idea, is that this transfer of energy, hey, it's coming from the soft drink to the ice. Okay? Did I do? Oh, that's confusing. All right, so understanding systems and surroundings. Now, describe how the arrangement and the motion of the particles in each system change from initial to final state. Really, guys, all this is the phases of matter stuff that we've been working on since Unit 2. All right? Solids, close together, moving slowly. Liquids, more spread out, moving faster. Gases, really spread out, moving really fast. And in this last part, we're going to use that again. But this is saying the graph below left shows the cooling curve for a substance as it freezes. On the graph at right, sketch the cooling curve for a larger sample. Okay? So the idea, what I was saying to some people yesterday when they asked me about this, I said, okay, let's picture How long does it take a cup of water to freeze compared to, say, a lake of water? Okay, a lot longer, right? Or even say if you're trying to freeze a gallon of water compared to a cup, would they freeze in the same amount of time? No. So if I look at the larger sample, it's going to cool slower. Eventually, it's going to get to that same point, that freezing point where it's going to flatten and then come down. All right. So which phase would label which phase or phases of the substance is present in each of the three portions of the cooling curve? So we've got the flat portion. We've got a portion at the end where it's decreasing again. And we've got this beginning part where it's decreasing. So if it's freezing, what must this first part be? Liquid. This is freezing. And this is solid. So that's what you do for that. Some people miss this last one. I don't know if you just ran out of time or didn't understand it, but the arrangement and motion of particles, same thing. All right. So here we have the liquid where the particles are a little spread out. They're moving a little faster. But as I go to the right, they're slowing down, coming a little closer together, slowing down, coming a little closer together, slowing down, coming a little closer together, freezing, turning into solid. Those particles are starting to get really close together and aligned, kind of organized, and then we've got our solid. So now the particles are held in place. They're just vibrating back and forth quickly. But as we go farther down, slower, slower, slower. Okay? So that's the whole deal of this worksheet. So today I want to see you guys work on them on your own. Show me that you know this. I don't want to go to Friday and go, my kids are really good at this. And then we take the test and it's not good. Okay? So that's the plan.